Right, part B. This is our exciting, strange network of resistors.
The batteries one.
The batteries in this case. The 12 identical 1-volt batteries are connected into an electrical circuit as shown in the figure above. And it's worth just checking that they're all pointing the same direction, that they haven't been desperately sneaking switch one round. They do look all to me like they're pointing in the same direction, or same way round the circuit, clockwise. What will be the reading on the voltmeter? Right. I'm tempted to say nothing because they'll all be flat very quickly.
Yeah. Very good point.
Right, let's just draw this as an electrical circuit. And what I'd do, you've got it there on the exam paper, next door to it, just draw it out in circuit symbols. So we've got a string of electrical cells. Now they talk about internal resistance. So, internal resistance, where you've got a battery that looks like that. Okay, what we can do is model that as an ideal cell, which is a pure voltage source, plus an internal resistance R. So when you see internal resistance, just think about replacing the actual thing that you have in practice, the real cell there, with a perfect voltage source, which never runs flat, and a resistor, like that. So our circuit is going to look like that, with a resistor, and then with a resistor, with a resistor, and so forth around there, and we're going to have 12 of these. Okay, and now we've got resistors in here, some kind of resistance in there. We can see that the current is not going to be infinite.
Thank goodness.
Yeah. Don't try this one at home. Yeah. What would be the reading on the voltmeter? So when we've got the voltmeter, it's taking 3 of these. So and let's make sure we've got the right. We've got 3 R's in there. Okay. Kirchhoff's laws. I think called for on this one. Kirchhoff's first law, of course, is that current is conserved. It doesn't go anywhere, and the junction splits equally. We don't actually have any junctions at all in there, so Kirchhoff's first law is looking somewhat superfluous, because this voltmeter, if it's an ideal voltmeter, won't draw any current through there. Voltmeter is infinite resistance, yep, ideal voltmeter. So, Kirchhoff's second law says that the sum of voltages over components around a closed loop equals 0. So Kirchhoff 2, sum of voltages around a closed loop equals 0. Okay, we want to know voltage here, so the obvious loop to take is this one through here. So again, what I would say, perhaps just mark it on your exam paper. So label it second law loop, or Kirchhoff second more loop, so the examiner knows, right, he's considering going around there, it's obvious what you're doing. Okay, well, you may as well start somewhere. Let's start here, see what we get. So we're just going to go walk through this, come back there, and see what voltages we're going to get. Okay, so we're going to start here. Now we're going to, first of all, we come across a cell. Let's call it V cell. So we've got, so start at A. So we've got V cell. Now we're coming to a resistor here. The voltage over the resistor is going to be its resistance. Sorry, it's going to be the current through it. Oh, I'm going completely crazy here. Mine goes blank. That way. Voltage over the resistor is current times resistance. Just Ohm's law. Yep.
Yeah, is that an increase or a decrease in voltage through that one?
Okay, well, let's have a think about
does that matter?
which way is the current going to go? Well, if that's my positive end, the current is clearly going to go that way around the circuit.
Okay.
Okay, so if we say that A is the potential of 0 volts, and we can always choose a 0 somewhere, but we can only put a 0 at one point, and then everything else is going to follow. So if this were 0 volts, this would be a V cell, because this is a negative end, this is a positive end. It's increasing voltage going from that side to that side. Likewise, if we're going from here to here, now this current is lost. The voltage is lost as we go over there. So there should be a negative sign. The resistor isn't adding in potential as we go there. Then we come to another cell. So we've got B cell minus I times R. Then we've got V cell plus V cell minus another IR. Okay, now we're at that point there. Now we're going to go back there. Now we need to decide whether that's voltmeter, which way round we've got our leads, whether we're recording a positive voltage or a negative voltage. Let's say it's that way round. Negative side there, positive side there. Therefore we're going backwards through the voltmeter. So we're going to go minus the V on voltmeter. That is equal to 0. So just moving that to the right hand side. So we've got 3 lots of V cell. Take 3 lots of I times R equals V on the voltmeter. So the question then is, well, we can assume we know V cell, we can assume we know the internal resistance. What is I? Let's see where this one's going. I, of course, well, what have we got? We've got 12 cells. We've got 12 resistors. So what is I? So we've got 12 lots of V cell over 12 R, which is V cell over R. Which implies V voltmeter equals 3 V cell minus 3 lots of I, which is B cell over R, times R. You've got 3 B cell minus 3 B cell equals nothing whatsoever. That is kind of obvious, actually, when you get there, because just think about the symmetry of it. So having a voltmeter there covering 3 cells is the same as bringing the voltmeter around to the other side, covering
Well, the other's 9.
the other's 9 cells. So, you know, the voltage over 3 cells is going to equal the voltage over 9 cells. So, and we know each one's going to be equal, so therefore, from symmetry they've got to be equal, so therefore they've got to equal 0.
That's good.
We could just argue it like that. So, I'm sure a calculation like that will suffice to give you what the result is, but also you could argue that from symmetry. You could say that you know, the V on the voltmeter, the 3 cells, has got to equal V on the voltmeter for 9 cells, and you can just draw that diagram to show that what we've done is flipped it on the other side of the diagram. V for 1 cell is, or V for each cell is constant. Which implies V must be 0, or V voltmeter. Quite long.
That's good.
Solve that one.
Another way of looking at it perhaps could be that the voltage. Oh no. Does that imply that there's no current flow as well? Or am I?
Well, there's current flowing, yeah. I mean, there's got to be current flowing around there. You've basically got a short circuit of batteries.
Yeah. It's still very unsatisfying to me for some reason. I can't visualise all of the things that are going on in the circuit.
It's kind of symmetry, really. You know, if you start there and then you walk over there, does the voltage go up or down?
Yeah.
Well, if it goes up, then it'll go up. You get a higher voltage when you end up there.
So, is that saying that it goes up and then down by exactly the same amount?
Yeah, so it goes up over there and then down
by the same
resistor by the same amount.
Yeah. So
of course, in reality, you can't separate these out. You can't stick a voltmeter in there because this is just the model of that.
It feels better, but it's still awful in my mind. Yeah. But it is a lot.
Another way of thinking about it, you know, you short circuit a battery.
Yep.
You know, just short circuit that. What do you get? Well, you know that the voltage over it must be 0 because those two ends are connected. The voltage over it must be 0. This is just a wire.
Yep. If you consider no internal resistance on the wire.
No resistance on the wire, yeah. Where's the resistance? Well, the resistance is buried in there.
Yeah.
So there's still current flowing through there, but the current flows such that the amount of voltage lost over the resistor is equal to the source.
Yep. Right, that's good.
So, when it's one of these, when you tackle it, do the equations, you start thinking, well, actually, this was more obvious than we thought.
Well, you could also consider the energy, so the energy gained by, voltage is energy per charge.
Yeah.
The energy gained in the cell is lost exactly in the resistor.
Yeah.
As heat or whatever.
Well, it's got to be, otherwise. Yeah. Otherwise, as this current goes, it keeps gaining energy.
That's good. That's very good.
Yeah. Nice question. Certainly gets you thinking.